Okay, so today we're going over Bandle, which is asynchronous state machine replication made efficient. Hold on, let me get the Zoom chat window up on my other monitor quickly. So we have some bold claims. No more timeout tuning, easier to implement than Raft. One RTT on the fast path. No loss of availability, even if any F nodes fail at the same time. So that means it doesn't have the everything stops while we wait for the leader issue. Better at geo-replication than ePaxos, and higher in data center throughput than Paxos and Raft. So, yes, bold claims. So they have a couple things that they claim as sort of issues with what we currently use, which they've termed partially synchronous state machine replication. So that's Paxos, Raft, ViewStamp replication, etc. So they have timeouts. You need to tune them properly to ensure performance and correctness. It is correct if you set it too low. It just is not useful because you'll just be running elections all the time. The loss of availability after a leader failure, and that even the easy ones like Raft are hard to implement correctly.
Okay. So what happened to their claims? You just, in the first slide, they are falsified?
Yeah, these claims?
Yeah.
Yeah, so these are the claims that they're making. And then...
Yet these are the facts, huh?
These are their claims.
Right, but the next slide is the facts, and then their claims don't...
Well, this is asynchronous, not partially synchronous.
Oh, okay.
This is saying Paxos and Raft are bad. We need something better.
Oh, okay. Fine. I thought that this was your verdict on what the protocol needs to do. I'm sorry.
No.
I misunderstood.
No. This is the obligatory what came before is not good enough.
Exactly right. Yeah.
So, for asynchronous state machine replication, progress is driven purely by message delivery, not time, like with Paxos, Raft, ViewStamp replication, etc. They typically don't need a leader election, and they often require many messages to finish a round, which is the main issue that has prevented their adoption. So here we can see Rabia, which was a previous asynchronous state machine replication protocol. And it is optimized for use in data centers, but it requires 4 round trips in order to actually deliver a response. Because the output has to then be transmitted back to the client. So that is, I'll say, not ideal as soon as you have geo-replication involved. However, the property of progress being driven by message delivery is actually very nice because it removes timeout tuning. And it essentially means you will continually rebroadcast, and eventually you will get a message, and that will trigger the next part of the protocol. As long as you have not had so many failures that nothing can talk to you. In which case, if nothing can talk to you, you don't do anything, so you fail safe. As an added benefit, this means you are not mucking with timers and timeouts and interruptions inside of the execution of the protocol, which means you can implement it efficiently. So Bandle makes a couple assumptions that it's working off of. So it's targeting crash fault tolerance. N equals 2f plus 1, quorums of f plus 1, same as Paxos. Clients may crash, arbitrary number of clients. And then a TCP-like reliable in quotes network with finite asynchrony. So messages will be delivered at some point. This doesn't mean individual packets, but it means that you will, node A sending a message to node B will continue replying until it gets, it will continue sending the message until it gets a reply from node B saying, yes, I have gotten that. So possibly it will just not make progress because of that. In the same way that if you have a sufficient number of drops, Paxos will also not be able to make any progress.
Owen, can you give me a quick spoiler? They claim that they can be available even if with more than F failures, but
exactly.
they also say that we have quorums of F plus 1.
Yeah. So if F nodes fail, you will continue. You don't suffer any loss in throughput, even if F nodes fail simultaneously, because there's no leader.
Okay, not more than F.
Yeah. Yes. F or less.
Yeah. Okay.
Yeah. And it also assumes clients are able to order their own messages and provide a globally unique ID for them. So this means that clients need to actually serialize their messages. And then each instance of Bandle in a cluster can be given a unique identifier that has a defined total ordering, such as an integer, a UUID, something like that. So now we get into the actual protocol. So first you need to set up the cluster. So each process needs its unique identifier and a random number generator seed. And then you set up your communication channels, be that setting up TCP or just opening a UDP socket. And then you need to divide all of the log entries by sequence number, such that process PI is the leader of all log entries with an ID j times n plus I, such that j is a natural number. Essentially just partitioning the log round robin style among all of the processes. And this is done to eliminate the need for elections. So to commit an operation in Bandle, what you do is first, the process which has received the operation from the client picks the next free log entry it's a leader for, and it proposes that operation as a value for that entry to all other nodes. And then all processes that receive that, including the one which just proposed it, pass one to the flash BA instance, which we will treat as a magic agreement box for now, associated with the log entry and the first round, because you may need to have multiple rounds of this in order to actually converge in the presence of in the presence of sort of node failures. So all processes then wait for either the flash BA instance to output or for n minus f higher log entries to be committed. And if n minus f higher log entries are committed, in the next round of flash BA for that slot in the log, switch to a 0, which will end up aborting that round. It will end up aborting the attempt to commit the operation, and the process which initially proposed the operation will have to retry. And this is used as a mechanism to stop a single slow node from holding everything up. And it was generally judged by the authors that if you get to F entries ahead of the node, or of the log, or sorry, F+1 entries committed ahead, then something likely has gone sort of wrong. So this is your mechanism with which to skip crashed nodes. Because other nodes will proceed past this, fill up the log, and then go backwards and start skipping things. So if flash BA outputs a 1 when it's all done, you commit the operation. Otherwise, write a no-op, retry the proposal.
Oh, and I'm not able to see the connection to F+1 more log entries be committed. I mean,
this is, I think, I got the feeling it was chosen sort of experimentally, because you can't have more than F+1 because you need F+1 functioning nodes
yeah.
in order to continue. So what this essentially says is if every other functioning node has committed something and you still haven't managed to fill in your slot, you lose the slot and are likely judged to not be functioning correctly anymore and in a failure state.
Oh, but if all the nodes are not sending proposals at the same rate, like
yeah, so that is something that they did deal with in the paper. It causes interesting effects when you have skewed latency between regions. If you have georeplication, it essentially forces either turning off pipelining, or they have a mechanism to help decrease latency by having nodes having a node assume a log slot when it knows what's being proposed and try to retry it. But that area of the protocol is a little messy.
This is a classical problem that Mencius experiences, right? And all you need to have is like not even like skewed latencies between regions and whatnot. Skewed workload. One region doesn't have enough clients pose enough work, and all of a sudden you have all of these instances owned by this particular region that just don't get filled because there is nothing to fill. Like there is nothing wrong with the region. There is nothing wrong with the latency. You may just have a workload that's absent in the particular region.
Yeah.
And
Yeah. So they solved that with I will call it a fuzzy fix, where if a process doesn't have any work to do and its slot is upcoming, it should propose a no-op.
How does it know its slot is upcoming if this is asynchronous?
So it can see sort of progress in the log. And I think here you probably would use timing to try to figure out like how much, like, am I likely to get a new operation before my round comes up? Or am I going to be blocking everything unless I commit a no-op?
So did they do any experiments on this?
Yes, there are evaluations on it with both georeplication and throughput tests in the same data center.
Okay, let's wait until then.
Yep. So now we need to look inside the magic box, because most of the smarts of this algorithm are in here, since this this commit process is fairly trivial. If you assume a 1 returned from flash BA means there was consensus and yes, this is okay. So it's a randomized binary agreement with a 1 round trip time happy path, 1 instance per log entry. It's round based and has a suggest and a propose phase in each round. That is the author's terminology. So a Flash BA instance can only enter the propose phase when it has an agreeing quorum in the suggest phase. And if a minority of processes suggest 1 minus B or not B in the first phase, B is the output. So there's also a promise mechanism where a process can, when suggesting or proposing B in a given round, make a promise to not, quote unquote, change its opinion for the round. Because this allows you to, so this mechanism allows some processes to send out their response and then say, oh, I actually am the thing preventing a quorum here, and change its response and send out an and act like it locally had always been the same thing, and then start acting as part of the quorum value. But that can help decrease the round trip time in certain cases. And so it's probabilistic consensus. So it's expected to be constant time, but technically there is no termination guarantee. I would expect a production system to eventually fall back to something that is not probabilistic, even if it might be slower. So there is also an important tie resolution mechanism. So there is a coin value, C sub R, that is used to converge in the event of divergence. And Bandle uses a common coin. So it's a fixed seed binary RNG, and then you mix in the sequence number and the round number. So in a given round of Flash BA, if PI has not suggested 1 minus B, and B is the inverse of the coin value, then PI gives B a promise in the first phase, which is it's a little messy, and they're doing this because they want a very particular property out of this. So in this case, PI won't suggest 1 minus B anymore. In the first phase, PI can only give a C sub R minus 1 a promise, so that all other processes have a chance to switch their suggested value to C sub R minus 1, but not vice versa. And C sub 0 is equal to 1 in all cases, since that enables the one round trip time case for the fast path. So in terms of how it collects these values, after you get F+1 suggest messages of the same value of B in a round, so these are messages that are sent out after a proposal is made. And in the ideal case, they will all be 1. So you're in a particular round, and the process inserts B into the value of its B set, essentially keeping track of, for all of my peers, what have they suggested for this phase. And then once it's collected enough messages, it can move into the propose phase. So if on the fast path, if p sub I gets f+1 suggest messages or f+1 propose messages for the same value of b, you have a quorum. You're done. You output that b. If there is not a quorum, then you have to go into conflict resolution. So what you do is you compare to the coin value. If all of the values are the coin value, output the coin value. If all of the values are not the coin value, then you need to output B with a promise in the next round. And then if the B set has mixed values, you need to suggest the coin value in the next round. And then once you've come to a decision, you stop actively participating in new rounds and just passively keep suggesting the same value whenever anyone asks. And that's how you can have, you can have all but one in a quorum fail, and then the value will make its way over to the other quorum. And it will do so with a promise. Yeah. So in terms of the evaluation.
Owen.
Yep.
The point of binary consensus here is to simply decide whether we want to keep the log instance or not, right?
Yep.
So essentially we decide in 0 or 1, and if we have some kind of conflict, we don't know what to decide, then we use the common coin and force some kind of arbitrary decision. We don't care which one.
Yeah.
Okay.
Yeah, and that coin value is used to sort of nudge towards convergence over time. And that's why it probably converges, but you could end up with a random number generator that just causes lots of issues. And this is the same input seed to the RNG for every single process, so they will all have the same coin value. It's more a matter of, do they disagree on what either the B set is or what B is. Yeah. So for the evaluation, they're using AWS, a T3 2x large. So it's an 8-core, 16-thread Skylake. It's a burstable instance type, so they're not getting full CPU at all times. 32 gigs of memory, about 2 gigabit baseline bandwidth, 5 gigabit burst bandwidth, 16 byte requests. And then the authors claim they're limited in throughput by the maximum number of rounds you can have in flight because of that property for failing a round if it takes too long to commit. You cannot have too many rounds in flight, so you instead need to do aggressive batching. Closed loop clients were used for latency tests, which is not ideal. And then the marshalling and unmarshalling of the requests had, quote, non-negligible overhead. So that wasn't really elaborated on, but the authors say that is why the leaderless algorithms did better when you increased the instance counts, because they were spreading out the work more. So if we look at geodistribution latency, this is 3 nodes, so California, Tokyo, and Sydney. And Bandle is doing pretty well here. It is fairly close to ePaxos. And the reason that Paxos is doing well here in California is because the leader is in California. So there's an extra round trip time to deliver the commit message back to Tokyo and Sydney. The previous asynchronous SMR algorithm has just kind of fallen over. And Mensis is also doing pretty well. When we increase it to 5...
What kind of workload is that? Do they specify like what's the throughput, what's the distribution of like workload between regions?
Nope. Yes, that is a point for discussion later. So 5 nodes, previous asynchronous algorithms fall over even more. And this is why a lot of people don't want to use them in production, is that this happens. And you can also see Paxos is starting to have some issues in regions where it's not the leader. And this also includes the introduction of an ePaxos with 0% conflict and 100% conflict. So obviously ePaxos does not do very well under high conflict rates. So that starts to become a problem. And Bandle is still doing reasonably well, typically beating Mensis, close to the conflict-free case for ePaxos. And then when we have skewed latency, which is Ohio, Virginia, and Sydney, I believe the paper said 11 milliseconds between Ohio and Virginia, and significantly more than that to Sydney for both of them. So Mensis just falls over. And then Bandle, as well as all of the other algorithms, managed to do well in the 2 closely connected regions, but the Sydney instance starts having issues.
Are these issues just latency, or Sydney cannot commit anything?
So I believe it is just extra latency, but it means that anything submitted to the Sydney node is going to have a high latency to deal with.
Because my napkin math doesn't work out. If we have n minus f as the threshold, the f is 1. So Ohio and Virginia can commit and always get the quorum. In the latency you have between Ohio and Virginia, you can commit probably like 5 or 7, log instances, or replicate, log 6, 7, 10 log instances for, 1 log instance from Sydney to arrive. So by the time, this like Sydney log instance arrive, Ohio and Virginia may already have decided in their like binary consensus that Sydney log instance is a 0, and it's a no commit. So my question is, does Sydney ever get to commit?
Yeah, so there was a... Let's see, where was that mentioned? That they had a fix for that, which essentially involved Sydney delegating. So in this example, it would involve Sydney kind of delegating operations to another node.
Okay.
In order to decrease the latency for retries, which is going to be kind of messy, but I think is really the only option to make this function well. So in terms of in a single data center, the throughput, and this is with batching, Bandle does very well. So here we get to see Mensis shine. And ePaxos, they don't list a conflict rate for this, so I'm going to assume 0%. And Bandle is hit Bandle for normal throughput where you just need a quorum is doing fairly well, and it is still managing to beat Paxos if it needs every single node to respond. So so your quorum is now n. When you increase it to 5 nodes, the leaderless protocols get to take a step ahead. And we see Mensis and Bandle out in front again, doing very good throughput. So this right here is what 1.9 million requests per second on a fairly small instance. So admittedly, I believe their state machine was not terribly intensive, but being able to push that number of items through consensus is helpful. And then if you turn off batching, we get to see what it actually looks like in terms of the rate you can do consensus at. So it ends up a little closer to 7,000-ish requests per second, but it's already started to fall over at that point. If you have 5 nodes, it gets a bit better due to hedging. So there are other important claims. So here we see Mensis and Paxos. So there's a leader failure at 10 seconds. And this causes issues for Mensis and Paxos. Bandle and ePaxos do not care about this. So I would say overall, they managed to achieve most of their goals. I obviously haven't had time to figure out if their promise of easier to code is true. But I think that this shows some promise because it helps deal with some of the issues that asynchronous replication previously had in geo-distributed deployments. So I think that is all.